All right, now, systems of equations basically are two equations or more, because again, we could have more, that are put together and considered one single problem. They're grouped together. So we could kind of think of this using some of the wording that we had from the inequalities as first equation and second equation have to be true at the same time. So what that means for us is, again, we're going to be looking for a solution because we're limiting this to just two lines rather than two inequality problems. Two lines, at best, are going to actually connect with one another, intersect with one another, overlap with one another somewhere. So when we say that we're looking for a solution, well, that could mean a point, could mean many points, could mean no points, where those equations, and for now two, but it could be as many as we might be given. So we say kind of in general, it's going to be a point that satisfies all of the equations that are in this system, in this grouping that we've been given. So kind of going back to the same sort of thread that we had when we started talking about equations. First of all, if they actually give us a point, can we decide yes or no if that works? Well, we want that point to work for every equation that they give us. They give us two of them. So we've got the 2x plus y equals 0, and when we plug in the values in their appropriate places, 0 equals 0, yes, yes it does. That's only half of our system. We have a second line, a second equation to worry about, the x minus 3y equals 5. When we plug those values into their appropriate spots, 7 equals 5, no, it doesn't. I don't care that it worked in one. I need it to work in all equations. So the fact that it didn't work in the second equation is really the deal breaker here. This particular point is not a solution to this system because it failed out here with the second equation. Now it's great if they have us checking points, but that's not the only thing. We're going to need to be able to talk about and figure out how to get those solutions on our own. So again, we want to run through the possibilities here, and just based on our experience with equations in two variables, based on our experience with lines, what we can do is we can either imagine or literally kind of sketch out pictures of how things can happen. So when most people just slap down two lines, they automatically think of two different lines, and those two different lines will usually, for the way that most people draw things, end up crossing one another, and they cross one another only at one spot, one point, which would mean that we would only have one solution. Some people are a little bit friskier in the way that they think, but they might still draw in two different lines, but this time, those are special lines being parallel. Well, if they're parallel and they're different from one another, they're never going to intersect, like the two lanes in a highway. They're just running side by side. Well, if they run side by side, then there's no place that they overlap with one another. So we would have no solution for that kind of system. And then the other possibility here is that if we draw two lines that end up being identical, those two lines would be parallel. They're always going to intersect. And so we would have infinitely many solutions. Every single point on what really amounted to one line, because they were identical. Two lines, really just one. So all the infinitely many points that are on that one line are infinitely many solutions. We have some special terminology that goes along with these ideas, which you might hear from time to time. So very quickly, to try to match up with the idea of lines being different or identical. Different lines would be independent. Identical lines would be dependent. And as far as the solutions, having a solution versus not having a solution, having a solution we refer to as consistent. Consistent there in that third case. Not having a solution we refer to as inconsistent. So we've got those two sorts of vocabulary words that we might have used when we talk about systems now and in the future. But what we really want to focus on, again, would be being able to solve things for ourselves. So we have three main ways of working with systems at this stage before we would make things any fancier. And we're going to really focus on the first two. We've got graphing and we've got substitution that we're going to focus on. But then we've also got this third method, which is alternately referred to as elimination or addition, depending on who you talk to or what kind of book or resource that you might look at. And the nice things about the names is that they at least give it some hint about what it is that you would want to do. So for graphing, not surprisingly, we're going to do some graphing. And because we're working with several lines, we're going to graph each one. So the suggestion that we have made in the past is that we would write each equation in the slope-intercept form, graph each of them, and then by eye, we are going to identify the point or points of intersection depending on how things just work out. We want to be mindful of our slopes. We want to think about parallel lines, either no solutions or infinitely many solutions if we come up with parallel lines. So we do want to make sure that we keep that sort of idea in mind for when we are graphing things. But again, the idea here is that we would have to identify by eye what we would have in our graph. So in this particular case, the first equation in our system is already in the slope-intercept form, which is nice. The second line would need to be rearranged into our slope-intercept form, so we could go ahead and graph that. Let's go ahead and use those same sorts of colors, the blue and the red, to graph those individual lines. So looking at the blue one, because it ends with a +2, that means that we would have a y-intercept of 0, 2. Because in between our equal sign and x, we have a negative. That means that we have officially a -1, which means that more officially our slope is -1/1. So we could interpret that as right 1, down 1, right 1, down 1, right 1, down 1. We could also interpret that as left 1, up 1. And that gives us plenty of points to be able to draw in our line. For the red, we have the -3 at the end, referring to the y-intercept for that being the 0, -3. We've got the number in between the equal sign and the x as the number 2/3. So that means our slope would read the 2/3, bottom number telling us move to the right 3 and up 2. Hey, look at that. Based on the size of our grid here, we can't actually get another point on that red line, but frankly, we've just found what appears to be exactly what we're looking for, and that is there where those red and blue lines meet one another. We have what appears to be our solution, our point of intersection, and that would be 1, 2, 3, down 1. So it seems like we are looking at the point 3, -1. We can, like we've done with other times that we've solved, check our answer. So we can take that point, like that earlier example that we did, plug it into the first equation, yes or no, it works or it doesn't. Take that same point, plug it into the second equation, yes or no, it works or it doesn't work. If it does in fact work in both of them, which I leave to you to do, then we can verify for ourselves that we do in fact have the solution and that it is correct. And you should find that that is exactly the case, that point 3 comma negative 1 is in fact the solution to this particular system. And again, this is great if we can identify by eye what that point of intersection is. Looking at a second example here, if we are working with the first equation, we have the 2x minus 5y equals 17, that we would solve for y. That means that part of what we would have to do is subtract 2x from both sides. That would then mean that we still have to divide by the negative 5 that's in front of the y. And since we don't want to get lost in anything, let's go ahead and throw in that extra little step before we slap down our slope-intercept form. Out in front, a negative divided by a negative gives us a positive 2 over 5. And at the end, a positive divided by a negative gives us a negative, or a minus. Taking the second equation and doing the same sort of thing means that what we would have going on here is that we would have to only divide by 5 in order to arrive at our slope-intercept form. Dividing by 5, we get y equals 2 over 5 x minus 17 over 5, which is exactly the same equation that we just saw. So we can actually go ahead and pop right into, let's see what color it was I used before, orange. These are the same equations. So we would say that we have infinitely many solutions. We don't even need to accomplish the graphing here. We can just flat out say that's what we've got going on without even needing to graph before I even worry about the graphing aspect of things. Recognizing these as being identical, as being the same, means that I would have infinitely many solutions. And we can actually be specific about what those look like. So just to jot in a little comment there, we can just say all points satisfying and let's just use the equation that we've got already on hand in slope-intercept form. Y equals 2/5 x minus 17/5. Those are going to be the infinitely many solutions that we have, the infinitely many points that satisfy that particular equation. We could have just as well referred to the first equation that they gave us, or the second equation that they gave us, because all of these are the same. They just are dressed up a little differently from one another. So really, we could have said all points satisfying 2x minus 5y equals 17. We could have said all points satisfying 5y equals 2x minus 17. Any of those descriptions are valid. Any of them are correct. And again, under the circumstances, we didn't even have to graph to recognize what we had going on. So that's an advantage to those special situations. But again, one of the comments that I've made here a couple of times is crucial with this method. Solving by graphing is only going to work for us when we can identify by eye what that particular point of intersection is. So really, nice lines, nice solutions are the things that we would be able to pick out. things that are a little bit more unusual, a little bit more difficult for us to identify by eye, are things that we're not going to be able to get from graphing, so we're going to have some sort of algebraic way of working things rather than graphical. So we need actual algebra steps that we would be able to work through and flat out come up with x is equal to this number, or y is equal to this number. And that way, whether they're nice or not nice numbers, we have exactly what we need. So that's where those other two types of methods of solving systems are going to come into play. The substitution and the elimination / addition method, depending on what sort of name you might see or hear from whatever source. We are again going to focus on substitution because this is a very handy one to have and it does the job for our purposes now. And we can go ahead and expand into the elimination / addition method later on if we need to, which depends on how far you go, whether you may need to do that. Now, the name substitution gives us an idea of where it is that we're going. At some point, we would want to make a substitution, and at some point as well, we would want to be able to deal with an equation that is more comfortable to us, which would mean, in this case, an equation that has only one variable rather than two. So, putting those kinds of ideas together informs really the first two steps that we've got. If I pick one of the equations that I have, and I solve it for one of the variables. So I've got a lot of choices that I can make. I'll pick the first equation, solve for x, pick the first equation, solve for y. Those are two possibilities. Pick the second equation, solve for x, pick the second equation, solve for y. I've got a lot of different choices that I could make there as far as completing that very first step. But once I have made that decision, then I'm stuck with whatever else will come out of that based on the remaining steps. The second step there is the substitution step. I'm going to take the equation that I didn't use in step one, and I am going to make that substitution. Let's take a look at an example here while those descriptions are still on the screen so you can start to get a bit of a feel for what's going on here. So let's say in this particular example with these equations, x plus 7y is equal to 1, 5y minus 7x is equal to 20. I've got these four different choices that I can make. Pick the first equation, solve for x. Pick the first equation, solve for y. Pick the second equation, solve for y. Pick the second equation, solve for x. I can make any of those four choices in order to complete that first step, which simply again says solve one of your equations for one of your variables. Well, out of those four choices, the quickest thing for us to accomplish would be to solve that first equation for x, which is why I've made that particular choice here in the steps we're working out this particular example. Subtract 7y from both sides, and there we go. Now that I've used that first equation, I'm not going to use that with my second step. In my second step, I'm going to have to use the other equation, that 5y minus 7x is equal to 20. I'm going to replace the x with what I discovered from completing my first step. So I'm going to replace that x with the minus or negative 7y plus 1. So 5y minus 7, instead of the x, I'm putting in that negative 7y plus 1 equals 20. So what we can see here literally in this example is that we now have an equation where the only variable that shows up is y. So we can go back to our skills for solving equations from a while back and say, well, all right, there we go. We're going to solve that equation the same way that we've solved equations in the past. Now, with the way that things can turn out that we saw earlier from the graphing as well as just from the general discussion here, this result from step 2 could end up containing no variables. In that case, we use those comments that we used before. If my variables have gone away and I have a true statement, I would have infinitely many solutions. If my variables go away and I end up with a false statement, then I would have no solution. Now, those same sorts of things can actually turn up here, and those same sorts of comments are useful. So that would give us a way, in some of our problems, of actually just finishing things up and recognizing what it is that we have. If we have variable stuff showing up, and we go ahead and solve that, then we're going to have half of our solution, half of our point of intersection. And we're going to need the other half, which we can get from our result in step 1. So in this particular case, we solve that equation there in the dark red, and we come up with y equals 1/2. We're going to take that 1/2, and we're going to slap that into what we had from the first step. What we had from the first step said x equals negative 7y plus 1. So if we take that, y equals 1/2, plug that in, we get x is equal to negative 5/2. We should have our answer, but notice there again in step 5, check, and then report. So if we go through the time and trouble of checking both of those, we should find that that is in fact the correct solution. You do want to make sure that you write those with the proper sort of ordering, and don't mess up and get your y's and your x's switched around. So we found y first, but that still means x comes first when we give our answer. So the x value that we figured out, negative 5/2, followed by the y value that we found, the 1/2. So we still have to give things in the appropriate order as we have with our other points in the past. So to take a look at a couple of these, starting with this next one where we've got the first equation that says 10x minus 5y equals negative 15. And the second equation says y minus 2x equals negative 3. What we've got going on here again from our first step are these different choices that we can make. We can solve the first equation for x or y. We can solve the second equation for x or y. And frankly, what would be the least amount of work for us is if we solve the second equation for y. Add 2x to both sides, we get y is equal to 2x minus 3. Now, because we use the second equation to accomplish that, that means that we're going to use the first equation, 10x minus 5y equals negative 15, and substitute the 2x minus 3 for y. So 10x minus 5 times 2x minus 3 in parentheses equals negative 15. When we simplify this by distributing and combining like terms, distributing combining like terms, notice that our variable stuff has disappeared, which means that if we very briefly go back up to those comments from before in green, if we have done this work and we do not have any variables, then we have a true statement or a false statement. Well, in this particular case, we had 15 equals negative 15. That's false. Let's just kind of highlight that with a little bit of color to pop out there. That's false there. So this system has no solution. Just like the equation itself that we were trying to solve, the equation by itself here that we had, the 10x minus 5 parentheses 2x minus 3 equals negative 15. That equation has no solution. Because it has no solution and it came from a system, the entire system itself has no solution. We're done. That's it. There's no other work that's involved when we have some of these special kinds of situations that show up. But just, again, for a little variety and a little bit more of experience with working through things, let's do one last example here where, again, we've got our two equations, we've got our many different choices to make. First equation, 4x minus y equals 24. Second equation, negative 3x plus 8y equals 11. I can pick the first equation and solve for x. I can pick the first equation and solve for y. Those are two of my options. I can pick the second equation and solve for x. I can pick the second equation and solve for y. So I have these four choices to make, or four choices that I could make. Which of those is going to be the least amount of work? Well, again, in this particular case, there is one of those four options that stands out as being better, less work, less effort than the others, and that would be, in this case, to solve the first equation for y. If we solve that first equation for y, we could say that, well, if we just go ahead and simultaneously add y and subtract 24 from both sides, 4x minus 24 is equal to y. So, in the second equation, replace y with the 4x minus 24. So we'll take that second equation, which starts with the negative 3x plus 8y equals 11. We'll then go ahead and replace the y with our 4x minus 24 and see what happens as we work through our steps here. If we distribute, that will give us negative 3x plus 32x minus 192 equals 11. Combining like terms would give us 29x minus 192 equals 11. Moving our constant stuff to the right-hand side would give us 29x equals 203, and dividing on both sides by 29 would give us hopefully something nicer than 203 divided by 209. And so if we pull up a calculator and see if we can luck out there on that, we do in fact luck out and get 7. This is half of what we need. X equals 7 is half of the point of intersection, half of our solution. So now we would want to use the x equals 7 in, well, from that very first step that we took, we have y equals 4x minus 24. that'll get us the y value that we need, which is the other half of our point of intersection. So y equals 4 times 7 minus 24, which would give us y equals 4. So it seems like, and again, as has been the case recently, I will leave the checking to you. If we check this out, we should find that this is in fact the solution to our system, and that is x first, y second. The point 7, 4 is the solution to this particular system.